Everyone. Uh, Thanks for coming to this talk. I'm very excited to tell you about WatchLink on behalf of my authors. So WatchLink is a sensor interface to connect multiple different external sensors to your smartwatches. It's low cost and low power. But before we go into details, like why do we need to connect external sensors to your smartwatches? Because smartwatches already has a bunch of sensors. The reason is most of the sensors in the current smartwatches are put by manufacturers for people for most common use cases for most people. For example, there's an IMU to do step counting, or there's a PPG sensor. But what if think about someone who spends a lot of time outdoors, and they might be interested in measuring their UV exposure. So they might be interested in having a UV sensor in their watch, which is something we are not going to see soon in a smartwatch. Another reason is, sure, we maybe need external sensors, but there are already ways to connect external sensors to your smartwatches. For example, via Bluetooth or Wi-Fi. But the problem with those approaches is that both these approaches consume a lot of power and need complex hardware. So that means you need to keep charging your battery of your smartwatch. So the problem we are trying to solve here is how do we get data from various sensors into your smartwatches in a low cost and energy efficient way? And the answer lies in a component already in the smartwatch, the ECG sensor. ECG sensors are designed to read tiny electrical signals from your heart. But what if we use the same hardware to detect other electrical sensors? We can encode data from those external sensors as tiny electrical signals, mimicking the electrical signals from the heart. And the watch's ECG sensor can read them thinking it's like a heart signal, but it could be data from different sources. The advantage of using this approach over other approaches is that it takes extremely low power to read data through ECG compared to BLE or Wi-Fi. Additionally, since now we have like a raw signal channel to the watch, we can design an encoding scheme of the data in a very simple and straightforward way, which can be implemented with just a few components, so the overall cost also goes down. Here's a demo of how the ECG interface can be used for data communication. On the left is a person taking a regular ECG. The signal looks like an ECG. But on the right, we are injecting a sine wave using a function generator in the smartwatch. And the app running is a native ECG app on Apple Watch. And the watch can read it easily and shows a sine wave. So having known that we want to explore this technique, we did 3 different explorations to understand what are the communication channel characteristics here. So we looked at signal types, signal frequency, and amplitude. For signal type, and for this characterization, we used 2 popular smartwatches, Apple Watch 9 and Pixel Watch 2, which were the most recent at that time. So in the first exploration, we found that the watches are good at reading AC signal, but does not read DC signal. And whenever you're trying to have a DC offset, it will send it to 0. We also found that both the watches could read a signal up to 20 hertz. And it's important to note that here that Apple Watch samples at 512 hertz, whereas Pixel Watch samples at 250 hertz. So the actual signal received is can be much higher in bandwidth, but the signal we get from the watch is post-processed, and the manufacturers probably do a bunch of post-processing on it to optimize it for heart signals. So the performance of this signal can be even improved beyond this. For amplitude, we saw that the minimum voltage you need is 100 microvolts, which is like so small, but it still detects. And the maximum you can go is like about a few millivolts. One thing we also noticed that the signal you get out from Apple Watch is very clear, very nice. From Pixel Watch, there is sometimes some noise associated with it. So based on this kind of characterization and the need for a simple encoding scheme, we decided to use frequency modulation. And the reason for that is like frequency modulation can be implemented in a very simple way, just with a few components. And when we talk about frequency modulation, one important thing is frequency resolution. So frequency resolution is essentially how close can 2 frequencies be close to each other and the receiver still differentiates between them. And we did a bunch of experiments and we found out with both these watches, you can go as close as 0.05 hertz. So this parameter sort of dictates what is the how well the signal or what is the dynamic range of this sensing technique. So having figured out the technical details, we went into understanding, so this is going to be used by a user. What are the different parameters which a user would think about? So first one is, how do they want to connect sensors to their watch? And the second thing is, how is the connection made from the sensor to the ECG interface on the watch? And we'll talk more about this. So think about user interface preference. So based on individual users, some people might want to they're okay sticking something to the strap of the watch. Maybe some people don't want to because they want to keep changing their strap. Or some people don't want to connect anything to their watch and have something independent. So for that, we have watch strap sensors, which sticks onto your watch, existing without any modification, any other modification to your watch. Then we have case sensors, which has all the circuitry included inside the case, and it can be just latched onto your watch. And finally, we have companion bands, which goes side by side on your watch. And this is mostly very useful for sensing reasons, like for occasional use, for example, like breath alcohol sensor. The second design aspect was, how do you create a physical connection from the sensor to the watch? And this mainly depends on the application you're doing. For some applications, you want to make continuous measurements. For example, if you're outside and you want to make UV light measurements, you want to know at all times how much was the exposure. But versus for breath alcohol, maybe you want to do it once or twice. So it depends on whenever you want continuous and all-demand. So for continuous, the simplest way is to directly have a galvanic connection from the sensor to the ECG interface. And in both these watches, the ECG interface is the watch's crown. Another way to do this is actually making a physical connection by using your fingers from the sensor to the watch, and the data flows through your body, through your fingers to the watch. So this for continuous, they make a sliding contact and a ground connection, and for on-demand, the data flows through your fingers. So this is the overall characterization and design, and we want to show a few examples, which shows examples of various of this different setups and different scenarios. So there are 4 examples, and I'm going to go one by one. So first one is a temperature sensor. So you might think some smartwatches already have a temperature sensor. Why do we need more? The reason for that is it's well known that temperature sensing on the wrist is not a good location to sense temperature. It is not well correlated to the core body temperature. A better place to sense temperature is a forehead or the ear. So in this sensor add-on, you can stick the sensor to your strap, and whenever you want to take forehead temperature, you can just touch it to your forehead. The second example is a UV light sensor. And in this case, we have designed the circuitry such that it goes entirely inside the watch case. And the cool thing about this is also that there's no battery in this sensor. It runs on harvested ambient light using photodiodes. The third example I'm going to show is a companion sensor. So it goes as a separate band you wear. And here the user is trying to make a measurement. She blows on the sensor and makes a physical contact using their fingers to send the data from the sensor to the watch. The last thing is buttons. So we always face this problem that smartwatches have small screen. People have fat fingers. How do we interact with it? So one way to do it is adding additional buttons to it, which could be shortcuts or could be used for navigation based on what the user wants. So these are the 4 examples I wanted to show. All right, so this is towards the end of my presentation. I have a live demo. But I don't know if you guys would be interested in it. Let's do it then. All right, so. All right, so this is my prototype of the WatchLink. I hope you can see it well. There's a little shadow here. So the prototype I have are buttons. So I have like 4 buttons here, which can be used for anything you like. So the demo I'm going to show is I'm going to open the ECG app and show you the raw signals. This sensor is making a sliding contact using this 3D printed part with a small spring contact. So I'm going to open up the native ECG app on this watch. This is a Pixel 2 watch. And what you will see is sort of a square wave initially. Oh, let me do it again. Right. And this is like the default signal the sensor sends from the, and whenever I press any other button, the information is encoded in frequency. So you will see a square wave with a different frequency. Let's try that. See, the frequency changes. So whenever I press the button, the frequency should change. And we have 4 different buttons. So if I press any other button, the frequency should be different. So this is button 1, and this is button 2. And based on the frequency, you can identify which button it is. And yeah, that's all from my talk. Thank you so much. Happy to take questions.
Hey, great talk. Really like the idea. So I had like 2 small questions. Like the first question is like, would the system still work to like detect the heart rate when this thing is working?
Yeah, I think that's a very important consideration. So 2 things. There are 2 ways to do it. One simple thing is whenever you want to do like the actual ECG measurement, you just switch up the sensor. That's like the simplest thing.
Yeah.
Or you can do, the second thing is you decide on a frequency range or a modulation range such that it does not interfere with the heart signals.
But is the thing right below the thing, right? So you might have to pull off the sensor.
No, you don't have to.
You don't have to.
So
Okay.
it only makes a small contact. So
okay.
You still have a good contact with the skin.
Okay. And the second question was like, I mean, I get the idea of using the ECG. Like, would it benefit like just putting the 2 wires directly to the USB? Like, would that still work? Like, just connect the 2 wires and just communicate using that instead of using like the heart rate. Like, I understand it's like no contact kind of thing, but like just putting the 2 wires, connecting it using a single wire would communicate the information.
Yeah,
right?
I mean, that will be a perfect way if there's a communication channel USB, but I think most watches don't have a USB port. And
no, but they have those things for like programming the
right.
thing, right?
So I think, okay, if you want to do it that way, so first of all, like you'll need to get access to it because most watch manufacturers don't give it to it. But
Okay.
even if you figure that out, I think the problem still remains that to maintain that kind of communication, high level of communication, you will need a microcontroller, an advanced protocol, USB protocol, that will again call for like advanced like circuitry. At that point, you can do BLE or anything.
Yeah, thanks.
Yeah.
Hey, nice work. A very quick question. So when you were showing the signals, it seemed they were better for the Apple Watch.
Yes.
But the demo you did was on the Android. So
Yes,
is the reason mostly just ease of development, or is there any other trade-off?
No, it was just like ease of development. We had an extra Pixel watch. That's it. Yeah.